Hi all, welcome to the interview questions and answers discussion series 1 of power systems. So let's move on to the first question. Question: what is the primary advantage of using the per unit system in multi-voltage level networks? So let us have a look at the answer. Per unit system simplifies the calculations in the analysis of complex systems. That is, if you are using per unit system to solve complex systems using load flow analysis or power, if you are performing the short circuit analysis, the calculations would be greatly simplified. And next, it gives a relative magnitude information of the various parameters in the system. If you are looking at the various parameters like voltage, current, impedance, or power ratings of the various components that you are using in the system, per unit system helps to give you a relative magnitude information of those quantities. And also it eliminates the need for transforming impedances through transformers. That is, once you choose a common base value, a transformer's per unit impedance remains the same whether you look at it from the HV side or LV side. If you're referring to the actual value of transformer impedances, there is always a need to convert it or refer it either to one of the side, either to HV or LV using separate formulae. But if you are referring to the per unit impedance of transformer, the modeling becomes easier because there is transformers per unit impedance is only one value, either you are looking at from the HV side or LV side. Okay. So these are the advantages of using per unit system in power systems. So moving on to the next question. Under what conditions does the Ferranti effect occur? So let us look at the answer. Ferranti effect happens in long transmission lines during no load or light loaded conditions. The line's capacitance draws a charging current that creates a voltage drop across the line inductance that is in phase with the receiving end voltage. Okay, so this is the basic circuit for the explanation of Ferranti effect. So here we have the sending end voltage source represented as Vs and the sending end current Is. Then the line transmission line impedances are marked across the resistance and inductance of the circuit. Okay, and then at the receiving end, we have a capacitor that is showing the capacitive effect of the transmission line. And since we are assuming a lightly loaded line or a no load condition, the receiving end current would be generally zero. Okay, or there will be negligible receiving end current and receiving end voltage is VR. So suppose if I'm drawing the phasor diagram for this circuit, keeping the receiving end voltage VR as a reference. So VR plus the drop across the resistance and the line inductance, which should give you the sending end voltage, right? So VR is the reference voltage, that is receiving end voltage, that is taken as a reference. And at the receiving end, we have a capacitor, that is a shunt capacitor, to show the capacitance between the conductors in the transmission line. So the capacitor current is shown as IC leading your receiving end voltage. So VR plus IC into R, okay, which is in phase with the charging current. And then we have IC into X, that is 90 degree with the that is to show the reactance drop, that is drop across the inductance. So VR plus ICR plus ICX should give you what? The sending end voltage. So it is very clear from the phasor itself that your sending end voltage is less than receiving end voltage, or your VR is essentially greater than Vs. So this is a very abnormal phenomenon where your sending end voltage tends to rise due to the capacitive effect of the charging effect of capacitance in long transmission line. Under which conditions? Under no load or light loaded conditions. Okay, so hope the explanation is clear. Now moving on to the next question. Why does AC current tend to flow on the surface of a conductor? So let us look at the answer now. It is basically due to an effect called as the skin effect. Okay, skin effect. So what is skin effect? So if you take the cross section of a conductor, okay, if this is your the core or the central part of the conductor, so generally the interior strands, okay, here of the conductor would have higher self-inductance. Why? Because when AC current flows, the lines of magnetic flux will generally surround the conductor, especially near the core of the conductor. So here we'll have some lines of force which is surrounding the core of the conductor. So as more and more magnetic flux linkages happen around the central part of the conductor or the core of the conductor, this part would be having more self-inductance, and they're as in because they are linked by more magnetic flux. Okay, they are linked by more magnetic flux. So higher inductance means higher reactance. So this central part or the inner strands of the conductor would offer more reactance. So here the current would not flow much. So what happens? The electrons would tend to move towards the surface of the conductor. Okay, the surface offers least reactance, or it is the path of least resistance. The surface is the path of least resistance. So the current will flow over the surface of the conductor. And this effect is called a skin effect. And the fix, this is exactly why we are using the aluminum conductor, steel reinforced conductor. So in ACSR conductor, the aluminum part would be on the surface, and the reinforced steel, here we'll have the reinforced steel. So steel basically provides the mechanical support or stability for the conductor, and the aluminum, being a good conductor and as it is placed on the surface, is able to carry more current. Okay, so hope you got why does AC tend to flow on the surface of the conductor. Okay, yes. Now moving on to the next question. Give two technical reasons why three-phase is the global standard. So the answer is, first, constant power. Three-phase power is instantaneous and constant, whereas single-phase power fluctuates. So if you're taking a single-phase supply, see here we have voltage. Maybe this is your current waveform. Okay, this is V and this is I. So for each cycle, actually there are two zero crossings. So the voltage and current would become zero, you can say 100 times in every cycle, or two times in every second 100 times, and in every cycle two times. Okay, so power would also obviously drop to zero at these points. So if you're driving large industrial motors using single phase supply, the motors would be suffering from a lot of jerks or vibrations and instability, and just because the single phase power fluctuates. But instead, if you're using a three phase power supply, see, we have three voltage across each phases, offset by 120-degree. So even if at the zero crossing of, if you're taking the what you say, the zero cross, if at one instant if the power drops to zero in one phase, the other two phases are live. So power is not pulsating, it is instantaneous, and you'll have some definite constant value at each instant of the three-phase power supply. So that is one reason. Next reason is that self-starting. Okay, that is three-phase supplies create a rotating magnetic field called as RMF. So if you are using three-phase induction motors, uh, very commonly in industries, it will allow motors to start easily without the need for extra capacitors or auxiliary windings to start the motors. So in this case, it it uh, it is a great advantage for operating the machines. Okay, you can easily start the motors without needing to spend for the extra cost of extra capacitors or windings to start motors if we were using single phase supply. Okay, and moving on to the next question. What is restrike voltage in a circuit breaker? Okay, let's see the answer. After the current reaches zero and the arc is momentarily extinguished, the transient voltage that appears across the contacts is called the restrike voltage. So if it rises faster than the dielectric strength of the medium, the arc reignites. Okay, so here we have the voltage and current waveforms during the arc interruption period of a circuit breaker. So at the current zero, you can see that there is a restriking voltage, that is a high transient voltage that appears across the contacts of the circuit breakers. So this transient voltage that appears across the contacts of the circuit breaker at or near current zero, this is a current fault current waveform. So at that zero crossing, you can see there is a transient over voltage. So this voltage is called as restriking voltage. So once the transients have died out, the other voltage that is remaining, that is the normal power frequency RMS voltage that is existing, is called as recovery voltage. So don't confuse with restriking and recovering voltage. So if this rate of rise of restriking voltage called as RV, if it is greater than the dielectric strength, rate of rise of dielectric strength of the medium, the arc will reignite and the current interruption will be, or the arc interruption will be a failure. Okay, yes. So hope all the questions discussed in this video session is clear to you. So thank you. Keep learning.